It is physics again. And today we are talking about deformation of solids. So deformation of solids, this is a solid and it has been deformed because it didn't used to have this shape. Stuff has happened to it. This is a solid and I'm deforming it by doing this, and now I'm restoring it back to its original shape. Deformed, restored. Deformed, restored. You get the idea. Let's start with a few definitions. Strength. What is strength? Strength is the measure of how much force can be applied to something in newtons, how much force can be applied without it breaking. So, how many newtons can be applied before something breaks? And the only way to find out is to keep applying force until something breaks. And just before it breaks, well, that's the amount of force, that's the measure of strength. So concrete has a high compression strength, meaning you can't compress it very easily at all, but it's got a very low tensile strength. Tensile, tension, pulling apart. Okay? Reinforcing steel that they put inside concrete, that has a very high tensile strength, hard to pull apart, not very much compression, but concrete and steel together is very strong with compression and with tension. There you go. So now you can go and become an engineer because you know all about concrete. Stiffness. Stiffness is the measure of how difficult it is to change the shape of an object. So something like this is not stiff because it's easy to change the shape. Something like this, very difficult to change the shape. If I bit it, I'd just hurt my teeth and I wouldn't change the shape of this object at all. Brittleness. Some objects are very stiff but they're also brittle, meaning it takes a lot of force to break something, but once it breaks it just it fails, like a ginger nut biscuit. They're very stiff. It takes a lot of force to change the shape, but once it changes it totally fails. Just kabing, it's gone. And then there's ductility. If something's ductile, it will eventually snap, but it can be drawn out into a wire. So copper is a good example. Copper can be just drawn out and drawn out and drawn out until it forms a long wire. We say it's ductile. Now there's another term too, that's elasticity. So say elasticity. Alright, elasticity is the property that allows a material to regain its shape after it's been distorted. So here's my rubber band, here's its original shape. This is an elastic material because, well, you know, it's called an elastic band, so it's elastic, but it regains its original shape. However, I could put enough force on this rubber band that it does not return to its original shape. It would snap and then it would hurt my finger and I would say ouch. But elasticity is the property that allows a material to regain its shape. If it regains its shape, we say it's an elastic. It is an elastic material. If it doesn't regain its shape, then it's not an elastic material. Okay, let's do a little reminder about Hooke's law. Everyone's heard of Hooke's law. Hooke's law is when you, again I'll use the rubber band, when you apply a force, the amount of extension is directly proportional to the size of the force. Now let's just make sure we understand what extension is. This rubber band has a particular length. Now I apply a force and it's got a bit more length. The extension is the extra length. It's that extra bit between there and there. The extension isn't the length of the whole thing. If you use the length of the whole thing, you'll get all your problems wrong, and that'll be unhappy for you because you got the extension wrong. So don't get the extension wrong, get the extension right. You need to know what extension means. Say extension 3 times and get it into your head. So again, here we have a spring, a certain length. We stretch our spring, it's now a bit longer. The difference is the extension. We call it delta L or we call it X, it doesn't matter. But the law, Hooke's law, is that force measured in newtons is directly proportional to length in meters, so that if you have a pen you can draw a line, and as the extension increases the force required to achieve that extension also increases, so it's a straight line like that. Doesn't look brilliantly straight. By the time you get to a maximum force F, you've got extension L. And that's what we call a directly proportional relationship. You know that. Now, there are one or two other things around this we need to be aware of. When you stretch a spring or a rubber band, you have energy stored inside this rubber band. Now we know Hooke's law, we know F, force, equals spring constant times delta L, the extension. Force, the force applied, that value F, is equal to the spring constant times delta L. The spring constant is just how stiff the spring is, or how much force is required to create an extension of a meter. It's a constant, it's a spring constant. So we know, we can find out how much energy is stored in the spring. We call it elastic potential energy. We also call it strain energy. Strain energy is elastic potential energy. Elastic potential energy is strain energy. They are the same thing. How do you find the amount of energy stored in a spring or a rubber band like the one I'm holding in my hand? Well, if you know the extension and you know the spring constant and you know the force, then you can do this calculation. So the way we think of it is, well, work done in stretching the spring equals force times distance. We know work done is force times distance. We know that because we've studied physics. Force times distance. But when you think about it, the distance is the extension, but the force is actually the average force throughout that whole extension. And the force starts at 0, it finishes at F, so the average force is here. It's half F. So if we say to ourselves, work done is average force times distance, then the average force is half K delta L. The average force is half times K delta L, because force, maximum force, is K delta L. So the work done is average force, half K delta L, times distance moved, which is delta L. So work done, or energy stored in the spring, is half K times delta L, which of course is half K delta L squared. Half K delta L squared. That is probably the messiest presentation you could ever come up with, but that is the formula, half K delta L squared. Alright, moving on, get rid of that. That is strain energy. That's elastic potential energy or strain energy. Finally, new term for you, the Young modulus. Now that's not a newer sort of modulus, and there's some old modulus. Young is just a guy who worked with materials. So the Young modulus is just equal to stress over strain. Now, I haven't told you what strain is yet, have I? No, I haven't. Strain is the ratio of extension over original length. So this is your original length. It's 5 centimeters. You stretch it out to 8 centimeters, so that's an extension of 8 minus 5. That's an extension of 3 centimeters. So the strain is going to be 3 divided by 5. So the strain is just the ratio of extension over original length. Young modulus, let me get something to write on. Young modulus, given this symbol, equals stress divided by strain. Now, what is stress? What is stress? Stress is exams, stress is lockdown, stress is COVID-19, but really at the moment stress is force per unit area. You think, hang on, force per unit area. I've come across that before. That's pressure. Yes, you're right, that is pressure. Pressure is pushing, stress is stretching. Pressure is pushing, stress is stretching. Okay, so if you're stretching something, then it's a stress. So the stress is force per unit area That's my phone going. Stress divided by strain. So stress is force per unit area. Strain is delta L over L. So Young modulus is stress divided by strain, which is force per unit area divided by extension per unit length. So that is the Young modulus. That's new for us. Finally, two more definitions. Let's just remind ourselves. Types of deformation. There's elastic deformation. Elastic deformation is when something returns back to its original shape. So it's whether the force applied or the stress applied is less than the elastic limit. The elastic limit is the point you get to where if you carry on stretching, it's either going to break, it's going to fail, or it's going to change shape permanently. And if something changes shape permanently, it's no longer elastic deformation, it's plastic deformation. So if I stretch something to the point that it starts off this long, I stretch it and it comes back, and where it finishes with zero force on it is a lot longer than where it started. That's not elastic deformation, that's plastic deformation. There we go. That will do.